In this series of videos I'm attempting to repair and restore this HP9845B vintage computer. So far in this series I've started going through the machine, carried out a few minor repairs, and I've now got to the point where I want to start going through and try and get it to boot up. It doesn't boot at the moment. It starts the process. It's getting further than it was. And in these videos I've been asked to show a bit more detail of some of the repairs. So in this video I'm going to go into a bit more detail than I normally would. If you want to see more of this sort of thing, then please leave a comment. But if you would prefer the repairs to move along more quickly, then again leave a comment. But I'll go into a bit more detail this time than usual, and we'll see if you find this interesting or not. So in the previous video I got as far as trying to resolve some problems with the keyboard. And to correct something I said in the previous video which was wrong, I said the keys are, I think I said they were magnetic reed switches, and they're not. They're magnetic switches, but they're kind of inductively coupled switches. The point I was trying to make was that they're normally fairly resilient to liquid ingress as long as they get dried out. Now unfortunately on this keyboard I think some liquid had got into it over an extended period, and there's a lot of green corrosion that built up inside the keyboard. Now I put the keyboard into an ultrasonic bath for probably a total of an hour and a half. It appeared to be cleaned up and I thought it was working. I had one of the keys removed and a number of the keys weren't working, and I assume that was just because I had the key removed. I'll explain why that could stop a number of keys working in a few minutes. But when I got round to refitting that key, it was the caps lock key, it wasn't toggling down, so I repaired that. As mechanical fault with it. And when I refitted the key, a lot of keys still didn't work. I mean about half of the keys. Because of the way this keyboard works, a single key can actually stop several other keys from working. So I just thought I'd explain before we go any further how these keys work. They are quite fascinating. It's one of these things that I don't know if HP designed these keys or the mechanism behind them, but it is quite interesting, and they are in theory very robust and resilient, but where they do fail is if they start getting corrosion inside. Now I did take the key that I'd removed apart. I did remove some other keys to repair them, and I did take some photographs, but unfortunately my camera decided to corrupt the SD card, and so unfortunately I don't have those images. If I need to take any more out, I will take some more close-up screenshots, but I think there are some images online of this type of key anyway. Now the way the keyboard works is fairly typical in terms of it's a scanning keyboard. So what we have is an array. We've got this fairly unusual driver chip, but what it really does is it outputs 4 bits for the column or row, depending on how you look at it. We'll call it the row count, doesn't really matter, and they go through a couple of decoders, and it selects one of 8 bits for each of the 4 values, and these are used to drive the rows. And then we have the column drivers, so I'm using 3, so the 4th input to this one is grounded, as you can see, and so this drives the column and row lines for the keyboard. And then down here we have this. Now this is a sense amplifier, and that'll give you probably some clue as to how this system works. And then it goes through this pulse generator circuit to generate the required signals to drive the keyboard. And we have this arrangement here to decode the special keys, so it decodes any special key codes and outputs them as shift or whatever. But one of the issues with this is that it's an inductively coupled key system. So just briefly explain how the keys work. There is some information online for this, so I won't go into too much detail. But each key is effectively arranged like this. So there's a magnetic core, so basically a ferrous core, a bit like in a core memory, but usually they're a lot smaller than the cores in these switches. And then you have a loop of wire going through the core, and then another loop of wire, and these two loops form two separate circuits in the keyboard. One is used to drive a current pulse through the drive wire, and that generates a flux in the core, and that is picked up by the sense line. Now, everything being equal, then the sense line would of course always pick up the pulse, and these are being pulsed all the time, so this is running continuously, and so you get a continuous stream of output pulses from the sense line. So to detect a key press, what happens is there are two fairly large magnets in the housing of the key, and these are attached to the plunger that the keycap is attached to, so when you press the key down, these two magnets come down fairly close to the core, and they basically swamp it, they saturate it, and that prevents it from being able to transfer these small signals across to the sense line. So it actually kind of works backwards. It stops the output of the sense line whenever you press the key down. Now, the reason a single key not working can prevent or make it look like multiple keys don't work is because these are arranged like this. The rows and columns are arranged in series, so in general there are 16 wide in series and there are 8 columns, so it depends how you look at it. But if you take one of the switches out, you effectively break one of these loops, and you break not only the drive loop but also the sense loop as well. So normally when all the keys are fitted, you'll apply a pulse between the row drive line and the column drive line, and then by doing that you'll get a current flowing through the entire circuit. That's all the keys that are on that particular circuit. Now, all these sense lines will provide an output, of course, unless the key is pressed down and the magnets are swamping the core, in which case you won't get an output. And what the system then does is it checks which particular row and column it was driving at the time, so it knows which one is not providing the output. And the output from the sense lines go through to the amplifier chip, and that's what we get out. But as I say, the problem here is if you remove one of the keys, then the whole thing will stop working. Now, the reason it wasn't working on this particular keyboard, as I say, is there was a lot of corrosion inside the keys, and you can tear them apart. It's not too difficult to take apart, it's quite tricky getting back together again. But what you're looking for is on each key there are 4 connections. 2 of them are for the drive. You can see we should be getting just a very low resistance, just an ohm or so, and then the other 2 are the sense wire, and again it's just a very short loop, so you'll get a very low resistance. What you shouldn't have is anything between the 2 windings, and that's what I was getting. At the moment it's showing about 13 mega ohms, but that's because it's connected to the rest of the system. We unplug the ribbon cable that's going to the driver board. I'll just lower the camera a little bit. So I've disconnected the ribbon cable that goes to the keyboard, and we can now read the key again. So we'll read between any 2 keys, and you'll see it's reading as open circuit, and that's what we should be getting. But I was getting resistances down to about 1.2k, and that was because of all the contamination between the 2. Because the output in the sense line is quite a low level signal, what was happening is the drive signal was going directly across all this contamination, and it was always registering on the output even when the key was pressed down. So that was preventing the keys from working properly, or it was preventing the coupling at all. It was basically damping down the sense output, and it looked like the key was always being held down. What I did is I traced which particular keys were causing the problem. I'll go through in a few minutes how I went about doing that. But once you detect which particular row and column is not working, you still have to, of course, detect which particular key or keys in that loop are causing the issue. And you can, of course, do that by attaching a logic analyzer or a scope to see which particular key is being strobed at the time when the signal is not doing what it's supposed to. So it's not particularly difficult to work on these once you get the general idea. Getting them out relatively easy. You can do that without dismantling the entire keyboard, just sort of solder out of the 4 connections, and then in theory you can pull the key out through the front. Just be careful, these boards are fairly fragile. So I did find a few faults with this. I've corrected those, found a few faulty keys, and so what we'll look at now is the signal that we can expect to get out of this keyboard. So I'll just move the camera. And if we now start looking at these signals being applied to the keys and coming from the keys, if we first look at the drive signals, then they're fairly large amplitude signals. These are what are being driven through the drive coils in each of the switches, and because they're all wired in series, you're not going to get a signal that's necessarily what you expect relative to ground, but you should be able to see the signals fairly clearly. What we get on the output is a continuous stream of output pulses. And you can see they are really direct coupled signals coming out of the keys. They vary in amplitude because of course the inductance of the keyboard is not consistent, and the switches do vary as well. But what we're looking for here is, if I put this into normal mode and then we try to press a key, it's going to be fairly difficult to see exactly what's going on with this. So you can see that if I do a single capture, all the keys are effectively returning a signal. If I hold a key in and do the same thing again, then I don't know if you can see this. It is quite difficult to pick this up and to capture it. But we've now got key, or a key position, that is giving us a different output, and this is the one that's being damped by our key being held down. Effectively, I was holding the key down and it's preventing the coupling at that point, and that's what's amplified by the IC on the driver board, and ultimately it's used to determine if a key is being held down. So this is what you're looking for. Now, as I said, you can trigger the scope or logic analyzer to trigger on the particular row and column driver values to look at individual keys. And the way I went about doing this is to use a feature of the machine itself to help narrow down which particular keys were causing a problem. So I'll flip the keyboard the right way up, and we'll start looking at some fault finding you can do, and a few shortcuts you can take with this machine to try and help you identify various faults. So I've got the keyboard the right way up. As you can see, I've removed the tape drives and a few other parts. They needed quite a lot of work before I can try using those, so we'll look at those in a separate video. I do have the 2 breadboard ROMs plugged in, so the machine is in a state where it's going to boot as far as it can. It's still not booting up, but I now want to just check that all the keys are working, and there is a fairly easy way to do this. If the machine does boot but you suspect there are faulty keys, what you can do is just take out the first ROM off from the PPU ROM card so it doesn't boot up properly, and what will happen then is the keyboard driver will start stacking up key presses, and when it's full it will beep every time you press a key. So we'll turn the machine back on. I'll start pressing keys. Now you do need to press keys that actually work, so just randomly move around pressing keys. So it's quite a few key presses, the buffer's quite long, so I'll keep pressing keys until it fills up. Okay, so it's beeped once, meaning we're getting close to the end of the line, or the buffer's filling up. It works a bit like a terminal telling you you're getting close to the end of the line. If we keep pressing keys, after a few more key presses, we'll get a beep every time we press a key. So now we're getting a beep every time we press a key, as long as the key works. So we can now go through and make sure every single key works. Now, when I was doing this, I found that various keys weren't working. There were actually two rows and columns that weren't working, and there were 3 faulty keys that had contamination in them. So I tracked that down by triggering the scope on the row and column drivers, figuring out which key was giving the poor signal, took the key out, took it apart, cleaned it, and now, as far as I can tell, every single key is doing what it's supposed to. So it's a shortcut way of making sure that every key works. Some keys will actually clear that buffer, so if we press the stop key, for example, it should clear the buffer and the beeping should stop until it fills back up, but again that proves that the stop key works. Also, I found, and you probably noticed in previous videos, that the stop and control stop weren't working the way they should do. Quite often when I pressed the stop key on its own, it was randomly triggering the halt LED on the printer driver card, whereas now it's not doing that. It is producing the right signal, and I have checked, and the keyboard driver is actually outputting the interrupt line as it should do. But now when we hold the control line and press stop, it's doing exactly what it's supposed to. So we can be fairly certain that something in the system is working better than it was. So incidentally, interrupts on this machine work a bit like Mode 2 interrupts on a Z80 processor. When a device wants to generate an interrupt with one of the 2 processors, it pulls down the interrupt line, and it also puts its device ID number onto the data address bus. In this case the keyboard is 0, for example, so it will pull down the 0 line to tell the CPU that it's interrupting, that it's the keyboard that generated the interrupt. So you need to check not just the interrupt line from a device, but also its particular device line is being pulled low when it wants to generate the interrupt. Otherwise the device won't know, or the CPU won't know how to handle the device. It won't know which handler to jump to. Okay, so we now know that all the keys are working. The latched keys now work as well. They do what they're supposed to. None of the keys stick down anymore, and every single key seems to work. And more importantly, the keyboard seems to be sending the correct data through to the processor. Still not booting. I want to see now how far we're getting through, and again there are some shortcuts we can do here to help us along a little bit. So again, I'll move the camera. So the machine is currently running, and you heard it beep when I powered it up, but if we powered it off, when we first start the machine up, it goes through a very rudimentary self-test, and it tests RAM. Now it's not really testing the RAM as such, it's just seeing if RAM is there. It's not going to tell you if any of the devices are faulty. In fact, it will do the same thing if you remove some of the RAM chips. But what it's doing is it's trying to figure out what RAM is fitted, and that's a process, it's a firmware process carried out within the processors. So we can actually see if that's working, because there is a fault mode it will go into if that fails, and more specifically how long it will take to fail. Now what we can do to provoke that failure is to simply unplug the drive from the startup fixture. So that's disconnected the vertical drive signal. When we now start it, what the machine will do is it will try to start up the 2 processors. It will go through the initial self-test to check for RAM, and it will do that before it starts trying to look at that signal. If the signal's not present, then what will happen is it will generate a continuous tone, but not until it's finished checking RAM. Now that's on the assumption that the system is able to run any code at all, so it's like a shortcut way of seeing if the systems are running at all. So we'll turn the power on, and after a second or two, because we don't have any RAM cards plugged in at the moment, just the 2 RAM cards for the 2 processors. So within 3 or 4 seconds we should get a continuous tone. If it does it straight away or not at all, we know that the firmware is not running at all. Okay, so it was about 3 or 4 seconds. Now we can go a bit further than this. If we plug in a RAM card, it should take a lot longer before the tone starts up, and it's again a good way to see if the machine is able to detect the RAM. If it can detect the RAM card, doesn't mean the RAM's working, but what it means is the firmware is running to the extent where it can actually identify the presence of a RAM card. So we'll plug this in, and the effect will be, if we put a RAM card in, is it will take a lot longer before that initial tone comes up, because the initial self-test will take a lot longer. So I'll get this plugged in. Okay, so I've got a RAM card plugged in, and we'll now try and power it up, and this time, if the system is working at all, it should take a lot longer before the continuous tone starts up. I've still got the drive line from our little breadboard disconnected. So as you saw, it took much longer that time. It was about 15 seconds, 20 seconds. And that means that it's actually going through and testing the RAM. Now if I put the second RAM card in, it takes even longer. But just to prove this isn't a fluke, I'll take this RAM card back out. We'll power the machine back up. And once again the tone starts much more quickly. I'll plug this back in, and the tone shouldn't appear at all, because it's going to hopefully get a bit further through the code. So this time we shouldn't get the continuous tone. And as you can see, it's doing what we would expect. It's not booting up. We're getting no activity whatsoever on the CRT driver board. That's this tall board on the left. And it is clear from other things, just looking around, that it's not doing what it's supposed to. The printer doesn't work. None of the other hardware seems to be alive, so clearly we're not getting particularly far through the startup. But what I want to do in this video now is see if we're getting as far as the LPU letting the PPU know that it's started up. So when this machine boots up, the two processors take it in turns to start up. The PPU will start up, it will get to a point in its startup code, and it will sit and wait until the LPU informs it that the LPU has started up. And so I want to test that now. An easy way of doing this is to use the logic analyzer. So I'll get the logic analyzer connected. We need to connect it to the PPU, because it's the PPU that we are trying to examine here, and that code is also at the beginning of the monitor program in the PPU. So I'll get the logic analyzer hooked up, and we'll see if the machine is getting that far through its startup. We'll also see if the LPU is reporting itself as having started. I've got the logic analyzer connected to the PPU, so I'll move the camera and we'll have a look at the logic analyzer, get the machine booted up, and try and figure out if we're getting through to a successful startup of the monitor. So I've got the logic analyzer set up so that it's capturing all data, so it's not demultiplexing the address and data bus. It's going to capture all data, so we'll see everything that's going on. And to get some idea as to what we're looking for, we'll go back to the startup code. And so what we're looking for here is the PPU startup. Now if you recall, the two processors look at the vertical drive signal from the monitor to determine if they're the LPU or the PPU. But early on, in fact, one of the first things the system does is it writes a value of 1 to a particular address in RAM. So this address is referred to as SCRFG. It's a startup flag. It just tells the system, or the system uses it to determine what to do next. And it writes a value of 1 to that address, and that is used later on. We'll see what that's for in a few minutes. It then goes through, checks the status of the vertical drive line, and if it's active, then this particular processor knows it's the PPU, and it will then branch to an address of 7A1E, which is the start of the monitor ROM. If we look at the code there, we end up at this point, and we can see that the first thing it does is to check the value at the address that the 1 was written to, and it checks to see if it's still a 1. If it is still a 1, it loops back and it waits. So it will wait in this very tight loop until the value in RAM changes from a 1 to a 0. And that value in RAM is actually changed by the LPU. So the LPU will clear this value to a 0 once it's started up. So this is basically where the PPU waits for the LPU to tell it it's started. So we'll try booting the machine up. We'll trigger on an address of 7A1E, so I'll just enter that. So we've got a trigger set of 7A1E when the init line is high. So we'll arm the analyzer, power up the machine. So we've jumped to the start of the monitor, so that's a good sign. It means the system is at least running to a certain extent. What you notice now is it will just keep looping round and round. So it's gone to 7A1F. We've got a value of 1 being read, so remember it reads data when this green line goes high, so the rising edge, and it's seen a value of 1 at that address, so that's the RAM address we were talking about. And then notice it's gone back to 7A1E, and we'll keep going round. So what I'm going to do, rather than scrolling through a great deal of code, is we'll now change the address on the analyzer to the address after this jump. So we'll go to 7A21, and if it gets to 7A21 we know that this value has been changed to a 0, and we will be able to check that on the analyzer. So I'll change the address, and this time we want 7A21. I'll turn the machine off, rearm the analyzer, turn it back on, and we have indeed jumped through to 7A21. So if we scroll across, we can see we're getting to 7A22. We'll just check the value there. It should be 3009, so we'll check that in our source code listing. And if we look at 7A22, then it should be 3009, and that's what we're seeing on the analyzer. So in other words, we've successfully got to this point where the PPU was starting its monitor program. It was waiting for the LPU to report it's successfully started up. Doesn't really mean it's been successful, of course, it just means it's got so far through its code. And then it's jumped through to this line, and it should now start the monitor program. System's not running, so something from this point on is not working, and that's what we'll start investigating in the next video. As I said, if you want to see this amount of detail, let me know. If you want me just to skip through to the more important points, then leave a comment.